Hi, let's talk a little bit about capacitors in parallel. There are some similarities between capacitors and resistors in circuits, and there are some properties that's consistent with both. For example, just like in resistors, the potential difference across each resistor is going to be the same, just like the potential difference across each capacitor will be the same. So if you've got a 12-volt battery, the potential difference across each capacitor is 12 volts. The charge stored on each capacitor could be different, just like the current through resistors in parallel could be different. And here's a good way to check your answer. The sum of the charge on each capacitor should equal the total charge stored in the circuit. That's a good way to check your answer, make sure you're on the right path. And to find the total capacitance, it's the sum of the individual capacitors. And so that is different. Resistors in parallel is the sum of the inverses of their resistance. But in capacitors, it's just simply adding up all the capacitors. That's because when we get capacitors in parallel to each other, like this, it's just like having one capacitor that is just really large. If we just kind of think about connecting those plates together. So adding capacitors in parallel actually just makes the effective plate bigger. So let's do some calculations with these and actually determine the total capacitance, the voltage drop across each capacitor, and the charge on each one. All right, let's start off with this one. So we've got a 220 microfarad capacitor and a 450 microfarad capacitor connected in parallel to a 24-volt battery, and we want to find these three things. So I want to first start off with a quick sketch of my circuit. I've got one capacitor, the other capacitor, and they're both in parallel to my battery over here. So this is my 24-volt battery, and this is the 220 microfarad. This is the 450 microfarad. And I just placed them there because that's the first one, that's the second one. And let's actually figure out these three things for this circuit. So to start off with, let's figure out the total capacitance. Well, since this is parallel, the total capacitance is simply the sum of all the capacitors. So in this case, it is 220 microfarads plus 450 microfarads, and that gives us 670 microfarads. And that's okay when we do this, but I actually want to put that into scientific notation. I want to take it out of this, and so that is going to be 670 times 10 to the minus 6 farads. That's the total capacitance. Now let's figure out the total charge of our circuit. So to do this, we have got C equals Q over V. We're going to use that equation a lot. It's almost like V equals IR in resistors. So our total capacitance is 670 times 10 to the minus 6 farads. You don't have to really simplify that. You just go ahead and leave it like this. It makes things easier. I'm going to figure out the charge, and my voltage is 24 volts. So 670 times 10 to the minus 6 times 24 gives me a charge of 0.016. Usually I stop and round it off there, but I'm going to go ahead and keep this just as a reference point. And now I want to figure out the charge on each capacitor. So we're going to do the same thing Now we know the voltage on each one is 24 volts because it's in parallel. So we know V for both of them is 24 volts. And so now let's do that for the first capacitor. So C1 equals Q1 over V1. Well, the capacitance for the first one is 220 times 10 to the minus 6. The charge we don't know, but the voltage is 24 volts. So let's figure out that one. 220 times 10 to the negative 6 times 24 gives me 5.28 times 10 to the minus 3 coulombs. That's for the first one. We're going to do the same process for the second one. C2 equals Q2 over V2. So 450 times 10 to the minus 6. The charge we don't know, but the voltage is still 24 volts. So 450 times 10 to the negative 6 times 24 gives me 0.1 or 0.0108 coulombs. And here's where we can check our answer. If we add up the two individual charges, so 0.0108 plus 5.28 times 10 to the minus 3. If we add those together, 0.0108 plus 5.28 times 10 to the minus 3, we get the total charge to be 0.01608 coulombs, which matches what we got there. So we know we got everything right. So that's a good thing, is we can actually check our answers for this. Let's do another one. On this one, we got 3 capacitors, a microfarad, a nanofarad, and a picofarad. That way I can do all the standard units here. Are connected in parallel to a 12-volt battery. We want to find these same 3 things. So I'm going to have my battery here. We got 1 capacitor, 2 capacitors, and 3 capacitors with that 12-volt battery. So each one gets 12 volts. Total capacitance. This is the sum of all the capacitors. So this time, I really can't just do the shorthand like I did last time. I actually need to write these out. So that's 4 times 10 to the minus 6 plus 80 times 10 to the minus 9 plus 200 times 10 to the minus 12. So see what we get here. 4 times 10 to the negative 6 plus 80 times 10 to the minus 9 plus 200 times 10 to the negative 12 equals a total of 4.0802 times 10 to the minus 6 farads. So mixing these doesn't really help you a whole lot. That dominates pretty much everything. But I'm going to go ahead and leave it out because you can see where we add these up. Let's figure out the total charge. So C equals Q over V. So in this case, we got 4.0802. I'll go ahead and keep that times 10 to the minus 6. The charge we don't know, but the voltage is going to be 12 volts. So 4.0802 times 10 to the negative 6 times 12 gives me a charge of 4.08 let's call it 9. Let's go ahead and round that off. Times 10 to the minus 5 coulombs. Let's figure out the charge on each capacitor. So C equals Q over V. For the first one, we got 4 times 10 to minus 6 equals Q over V, which is 12 volts. So 4 times 10 to the negative 6 times 12 gives me a charge of 4.8 times 10 to the minus 5 coulombs. And let's continue doing that for the rest of them. C equals Q over V for the second one, so 80 times 10 to the minus 9 equals Q over 12. And we get 80 times 10 to the negative 9 times 12 equals a charge on this one of 9.6 times 10 to the minus 7. And for the last one, C equals Q over V, 200 times 10 to the minus 12 equals charge over 12. So 200 times 10 to the negative 12 times 12 is a charge of 2.4 times 10 to the minus 9 coulombs. And let's add those up. So add 9.6 times 10 to the negative 7 plus 4.8 times 10 to the negative 5 gives me a total charge of 4.89, which we can round up to 4.9 times 10 to the negative 5, which is the same thing as that. So we still did everything correctly. Let's try one more that's a little more unusual. Okay, so on this one, we still have 3 capacitors. Now we don't know the voltage of the battery. We know that on the 20 nanofarad capacitor, we have a charge of this much, but I want to know the charge on all the others. So let's see if we can work on that. So we do know that C equals Q over V. We know this is in parallel, so the voltage on each one is the same if we knew what that voltage was. But since we know the capacitance and the charge, we can figure out the voltage. And it says this has been on for a while, so the capacitor should be fully charged. And that's usually what we'll find, is that they'll say something like it's been on for a long time, so the capacitors are fully charged. So 20 times 10 to the minus 9 equals 6 times 10 to the minus 7 V. So we solve for V, what I call the super secret metric. V comes out, and that takes its place. So when we do that, 6 times 10 to the negative 7 divided by 20 times 10 to the negative 9, we get 30 volts. So we got a 30 volt battery here. That means everything gets 30 volts. So now I can figure out the charge on each one. So C equals Q over V for the 80 times 10 to the minus 9 equals Q, we don't know, but we do know the voltage now is 30. So 80 times 10 to the minus 9 times 30. This one has a charge of 2.4 times 10 to the minus 6 coulombs. And the last one, C equals Q over V. 60 times 10 to the minus 9. Charge we don't know. Voltage is still 30 volts. Charge on this one is 1.8 times 10 to the minus 6 coulombs. Now what we can do is we can actually go back and figure out the total capacitance of this. So 80 plus 20 plus 60. Total capacitance is 160 nanofarads. And then we can take that and figure out the total charge from it and see if it matches these charges added together. If it does, we did everything correctly. All right, thank you for watching. Tune in again for some more videos. We'll do one for series capacitors. And like, share, subscribe. Thank you. Goodbye.